going to do an application of friction where we're looking at a block sitting up on an inclined plane, or rather a ramp. So the question is, if I put this block on a ramp that's tipped at that angle with that coefficient of friction, will this block stick there or will it slide down the ramp? So we have to go through and analyze the forces that are acting on this 50 kilogram block. So I'm going to draw a little dot there for my block. First thing I have, as always, is gravity going that way. And I have this surface that I'm working on. So if the block is trying to slide in this direction, then friction is going to point in that direction. It's going to try and resist my motion. And I have a normal force that's pointing directly perpendicular from the ramp. And so we've got this arrangement here where we have two forces that are perpendicular to each other. Those two meet at a 90 degree, because one is along the ramp and one is perpendicular to it. Then I have gravity that's sort of sticking around, not parallel to the ramp, but also not perpendicular to it. So I'm going to have to take that gravity force and I'm going to have to break it into components. So instead of the normal components of horizontal and vertical, I'm going to make one that is perpendicular to the ramp and one that is parallel to it. So I'll have force of gravity into the ramp, that's here, and I'll have a force of gravity that's along the ramp or parallel to it. So you can see that there is this piece that way. So I had this thing down here making a 10-degree angle in that corner. So I'm going to go through and I'm going to try and do a little bit of magic here. So if that's 10, then this is 80, because 10 plus 80 plus 90 gives me the 180 degrees in that triangle. But this corner here is 90 degrees. So if 80 is used up there, then there's 10 degrees in here. So whatever this angle is, it's going to end up in that part of my triangle as well. And so if I look at this, this, and this, I can rebuild a smaller triangle. This was the force of gravity. I had my into force of gravity into, and force of gravity along, with a 10-degree angle up here. So if I take that and I try and use some trigonometry in order to figure out the lengths of these sides, I can see that my into force is adjacent to the 10 degrees. So I'm going to use cosine for that, because SOHCAHTOA. Cosines are adjacent over hypotenuse. So cosine of 10 will be the adjacent force of gravity into divided by the full force of gravity. So my force of gravity into the ramp then will be this times cos 10. And similarly, if I want to do the along force instead of the into force, I'm opposite of the 10 degrees. So instead of using adjacent, I'm using opposite. That's a sine ratio. So sine of 10 is force of gravity along divided by the full force of gravity. So my force of gravity along the ramp, bring these up, would be mg sine 10. Now I think my marker has finally bit the biscuit, so I'll struggle through. It's a little squeaky. Okay. So now that I have those forces, if I were to add them to this diagram, instead of G pointing straight down, I have this force of gravity into the ramp, like so, he says, pausing for dramatic effect. The force of gravity pointed into, and the force of gravity that's along. Okay, now if I look at this arrangement, because the block isn't falling into the wedge or being popped off of the wedge, this force and this force have to balance each other exactly. So my into force is also the same size as my normal. Now friction, force of friction from earlier in the course was mu times the normal force. Now we didn't have that before, but I just figured out that the normal force was balanced by the piece of gravity squeezing the block onto the ramp. And that's sort of what friction needs, right? Is two things to be squeezed together. So if I fill that in, I end up with mu. The normal force is mg cos 10. Okay, I think I have everything I need in order to answer the question about whether this is stuck or not. My net force, so I'm going to take all the forces and add them together. If this thing is going to move, it's going to slide down the ramp. That means that this is the driver. So I'm going to start with my force of gravity along the ramp. And in order for it to move, it's going to have to balance or beat this force of friction. So it's being fought by friction. So if I pop my numbers in there, F net equals mg, and the along force is sine 10. My force friction is mu mg cos 10. If I can pop my masses in there, then I should be able to calculate this. So F net equals 50 times 9.8 sine 10, sorry, minus, my face is going to get in the way here, minus, the mu value is 0.2, mass is 50, g is 9.8 times the cosine of 10. So let's see, sine 10 times 9.8 times 50 gives me 85.09, and 10 cosine times 9.8 times 50 times 0.2 gives me 96.51. So my net force then would be negative 11.42 newtons. All right. Now, if you look at these numbers here, this one was supposed to be the amount of gravity trying to slide the block down the ramp. This one is the force of friction trying to oppose it. And if you look at what's happened here, the friction ended up being larger than the driving force. So I ended up with a negative for my answer. What the algebra is trying to tell you is that no, it can't go this way. It would have to go that way if allowed. But you have to be smart about that. Think about friction. Friction can't pull you up things. So in this case where you get a negative here, what you've discovered is that the system is in fact stuck. All right. So if you can take your force of gravity and break it into these components like this, then you're able to get a force of friction on an object that isn't flat, and then you can decide if the thing is stuck or not. So I'm going to clear this off, and then we'll try an example where it isn't stuck, and we'll think about where the energy is and how it changes as the machine moves. Okay, starting with this example, I have a 30 kilogram block sitting on this ramp, and there are 4 forces that are acting on it. The first one will be the force of gravity trying to drag it down the ramp, and I can calculate it with this thing here. So Fg along equals mg sine alpha, which is 30 times 9.8 times the sine of this angle here, 50 degrees. So I'm going to park that in the calculator, and I will get 50 sine times 9.8 times 30 gives me 225.22 newtons. All right. I will have a normal force pushing the block up, and it will be balanced precisely by this thing. So I can get that by throwing my numbers in there. 30 times 9.8 times cosine of 50 degrees. 50 cosine times 9.8 times 30 gives you 188.98. All right. The normal force is the same as the force of gravity into the ramp, which is 188.98. We already did that one. And I have a force of friction that is mu times the normal force, which happens to be 0.7 multiplied by this number here, 188.98, for a total of 132.29. So in this particular example, the force going along the ramp, right, there's my driver, 225, is greater than the friction. So this block is going to be able to slide down the ramp. If it can do that, then I should figure out what the acceleration is. So I start with my net force, F net, which is mass times acceleration, will be my driver force, 225.22, subtract my resisting force, 132.29. The mass of my block is 30 kilograms. And that, 225.22, gives me 92.93. So dividing both sides by 30, I can get my acceleration at looks like 3.098. Let's call it 3.1 meters per second squared. Okay, so I'm going to pop that back up here. Acceleration is 3.1 meters per second squared. All right. Now I'm going to let this block slide down this ramp. So it was initially at rest. It travels through 2 meters before it reaches the ground, and it's accelerating at that rate. So I should be able to get a time and a final speed from that. So I'm going to take a minute to clear off the board, and we'll do some kinematics. Okay, we're going to try some kinematics. With a VI, an A, and a D, I can get VF if I use this particular equation. So my V final is what I'm after. My acceleration was 3.1, and my distance was 2 meters. So VF squared will be 2 times 2 times 3.1, 12.4. And if I square root that, I end up with 3.52. And I'm going to save that up here for later. All right. So I need to get the time now. If I have a VF, a VI, and an A, I can do that using this equation. So 3.52 minus nothing is 3.1 multiplied by the time. 3.52 minus nothing is 3.52, so my time will be 3.52 divided by 3.1, which gives me 11.14 seconds. Sorry, 1.14 seconds. Okay, lovely. So I know that it's going to slide because I determined that the friction was insufficient to beat the portion of gravity pulling down the ramp, and I worked out an acceleration as a result of those imbalanced forces. I used my acceleration and the given information to figure out the final speed when this thing reaches the end of the ramp and how much time it's going to take to do it. The only thing left to worry about then is energy. So I'm going to have to consider two different states, one where the block is way up in the air and the other when it's at the bottom. So let's check that. First, I need to know how high this is. So I need h because I'm doing mgh. I have 2 and I have 50 degrees. Well, I can set that up opposite over hypotenuse as a sine ratio, so sine of 50 would be h over 2. So the height of that block is 2 times sine 50. Let's check that. 50 sine times 2 is 1.53 meters up. Okay, so when the block is way up here, the only energy it has, because it's at rest, is gravitational potential, mgh. It has a mass of 30 kilograms, Earth's gravitational acceleration is 9.8, and the height is 1.53 meters. So, let's see, that times 9.8 is 30, gives me something I wasn't expecting. 30 times 9.8 is times 1.53 gives me 449.82 joules. Okay, so in the initial position, there's this much energy to spend on whatever else is going to happen. At the end of the experiment, the block is down here. So it doesn't have any gravitational potential energy anymore, but it does have kinetic because it's been moving. So kinetic energy is 1/2 mv squared. At the bottom, I'll have 30 kilograms, and it will have reached its final speed of 3.52 meters per second. So 3.52 times itself times 30 divided by 2 gives me 185.86. Okay, so here's the thing. It had 449.82 joules of energy to spend, and it only spent 185.86 joules of energy getting faster. So the rest of that energy has to be accounted for. And if I look, I'm missing, well, that's almost 200. So it looks like I'm missing about 275 joules of energy. So you have to think about friction, because this thing was dragging. And what happens when you rub two objects together, right? They heat up. So some of this energy has been lost to friction. And the way you calculate that is you take energy is the force of friction multiplied by the distance that you traveled. So for this particular example, the force of friction, which I seem to have erased here, but if I check on my example, was 132.29. And it's gone through 2 meters worth of space. if I multiply these two things together, 132.29 times 2 gives me 264.58 joules. All right, now, some of this at the bottom is kinetic energy, some of it is lost for friction, but if I take this and add them together, my total energy would be that plus 185.86 gives me 450.44. Now, that number is the amount of energy we started with a little bit of a rounding error, right? This is basically 450, and so is this. So now that I've done this, I had a block on a ramp. First off, friction and along the ramp, the forces decided whether or not this energy could flow from one form into another. Once I decided it could flow, I used kinematics to find out all of its final speed and the time it takes to do it. I considered the energy that was available at the beginning, and I accounted for all of it at the end. The only thing left to do then is a power calculation, which is the amount of energy you're converting from one form to another, divided by the time it takes to do it. So that number, 449.82, divided by the 1.14 seconds, gives me not that, 449.82 divided by 1.14 is 394.5 watts. All right, so thing on a ramp, there's nothing that we don't know. We've got the energies all accounted for. We know the force gradients that made the thing move. We know all the kinematics variable, and we know the time or the power output of this particular machine. So I'm going to erase this, and we're just going to do a little thing about trying to make the block stick using the coefficient of friction and the angle. Okay, no numbers. I'm just going to do this in general. So I have a block with m worth of mass sitting on a ramp that has a coefficient of friction mu, and it is tipped at some angle alpha. So I had figured out before that the piece of gravity that went along the ramp was the mass times g times the sine of alpha. And that was true regardless of the ramp. It had to do with the geometry. So that's a thing you can just use. I also had the force of gravity into the ramp being very similar. It depended on the mass of the block, g from the earth, but it was cosine this time. And I was able to say that the normal force, the force pushing up on this block, had to balance the force of gravity into the ramp. So this was also mg cos alpha. And finally, the force of friction, which is mu Fn, ends up being whatever this coefficient of friction is, multiplied by the normal force, which is this. Okay. So, if we want this block to stick, the reason it sticks is that the force of gravity along the ramp, pointed this way, is exactly balanced by the force of friction pulling that way on it. So a block is stuck if the force of gravity along the ramp equals the force of friction. Well, I have some algebra for those things, so I'm just going to pop them into this little structure. So mg sine alpha equals mu mg cos alpha. Now, if I take a look at that, a few of these things are going to go away. So it looks like the m's divide out, and it looks like the g's divide out. So it doesn't matter how heavy this block is. The only thing that's left here are the angle that you tip the thing and how sticky it is. And that should sort of make sense, right? The stickier this is, the steeper the angle can be, and the size of the object doesn't matter. So if I write this with those things out of the way, I have sine alpha equals mu cos alpha. Now I'm going to pull a dirty algebra trick. I'm going to divide both sides by cos alpha, so that I end up with this. Now, depending on which math course you've taken, you might recognize sine of a thing divided by cos of a thing as a trigonometric identity. These two things, if you combine them that way, end up giving you the tan function. So what I have here is the sticking angle. So how steep can I make this ramp before something starts to slide? And it's just a direct relationship like this between the angle you tip the ramp at and the coefficient of friction. So if I were to just grab a random material, let me see if I check my table. So if I were to put an oak block on an oak ramp, if you put those materials together, their coefficient of friction is 0.3, according to this handy chart that I stole from the interweb. So if I put an oak block onto an oak ramp, I've already determined how steep I can move that ramp before the thing starts to slide. All I have to do is move my tan to the other side, so it's tan minus 1. Arctan is its proper name, of my coefficient of friction. So if I check that, here 0.3, and then arctan, I get 16.7 degrees. So because oak on oak is only this sticky, the steepest I can make a ramp is 16.7 degrees before this angle is too steep and the thing starts to slide. So the practice problems have a few questions about things on ramps, whether they're stuck or not. There's one that's stuck, one that's not. The one that's not stuck, it asks you to track all the energy, including the heat loss due to friction. And then there's some questions about sticking angle on the back. Good luck.